Hi, welcome to the first episode of Neuronarratives. I'm your seasoned host, Patrick, and today's topic, the magic behind the MRI scannings. In today's episode, we are honored to have Dr. Tomoki Arichi as our guest. Tom is the MRC clinical scientist and head of the Department of Early Life Imaging at King's College London. He's also a consultant in pediatric neurodiversity in the Evelina London Children's Hospital, along with many other titles under his name. Hi Tom, welcome to have you join us. First of all, would you like to tell us more a bit of what your current research is working on?
Yeah, of course. So we're working on lots of things, but really at the moment, in my lab and in my group, the thing that I'm most interested in is understanding how the brain first develops at the start of our lives, and particularly understanding how activity inside the brain first emerges and develops, and what that means, of course, for our futures. And the major motivation for this, incentive behind this, is that I also am a clinician. I'm a paediatric neurodisability consultant in the Evelina Children's Hospital, and so the motivation behind the work is really that what I'd like to do is to be able to understand why and which children are going to have particular kinds of difficulties.
Yes, of course.
So we can give better information to these families, and then ultimately to be able to understand how we can try and treat and improve things for these children. So the major modality that we do this is with magnetic resonance imaging. And so I do a lot of work where we are developing new methods to be able to get very detailed images of the brain. All the way in from fetuses all the way through into childhood, so that we can see what the brain's doing across that kind of crucial period in our lives.
Yes, of course.
And the kind of major motivation for that is that we know that that's a really key period in our lives. And that any kind of injury inside the brain at a time, or any kind of differences in how the brain develops in that time, really it sets the scene and the framework for the rest of our lives.
Yes, of course,
And so, just as an example, I look after a lot of children with cerebral palsy, and those children, unfortunately, have difficulties with their movement that last across their entire lifetime, and that's because they had an injury when they were a baby or around the time of birth. And they don't have any further injuries across their lives, but just because they had that injury due to some kind of difficulty at birth, right at the start of their lives, then unfortunately it means that for the rest of their lives they have difficulty with their movement. And so you can imagine being able to understand those kind of injuries and how it then has a knock-on effect on brain development is a very important thing to do, and the imaging is a very powerful way to do that.
Yes, of course.
So apart from kind of developing the methods, then what we're doing is then applying them, of course, to look at different groups of kids across different ages, and then we're using different kinds of MRI scanners to do that. So many hospital scanners, general hospital scanners, are of what we call a field strength of 3 Tesla or 1.5 Tesla.
We'll come back to that for more information. Go on.
But then we are also using scanners which have got much stronger magnetic field, what we call ultra high field scanners, and then we're also using what we call ultra low field, which are portable scanners, with the kind of trade-off being that when you move down to these kind of more portable low field magnets, then you would get less detailed images.
Yes, of course.
Whereas the opposite end, if you use ultra high field, then you get very, very detailed images. But the modality itself has got other different kinds of challenges, which I suppose we can touch on later. The ultra high field imaging is something which I'm very excited about, because it gives us much, much more detail, not just about the resolution of the images, so how fine the detail is, but also it's much more sensitive to particular aspects, and particularly function inside the brain, which means that we can really get much more granular detail about activity in the brain compared to using other scanners. The other two major things that I do at the moment is that we also using EEG to also study the electrical activity inside the brain. And we do some work where we acquire EEG at the same time as getting MRI images, and by doing that then we can kind of couple that information, so the electrical information about the electrical activity in the brain, together with the information about the anatomy of the brain and about the blood flow inside the brain that we get with MRI scanning. And we're doing that to study some really important and interesting things, like the way infants learn and the way infants understand kind of prediction about what's going to happen to them. And the other thing that we're doing is we're doing a lot of work with trying to develop tools which allow children who are slightly older to be scanned. Because going into a scanner when you're a toddler, when you're 2-3 years old, can be quite a challenging thing because you have to stay still.
Yeah.
It's quite a boring environment. It's also quite a different environment in terms of, it's a very unfamiliar sort of alien place that they're going to go in. And so what we're doing a lot of work with is trying to develop a virtual reality system, which we've done and we've patented recently, which allows children to sort of be immersed in a different kind of environment while they're having a scan done, and that not only allows us to be able to scan them and have them settled inside the scanner, but it also means that we're able to study different things to do with their brain activity by effectively presenting them with different kinds of visual stimuli and sound stimuli while they're using the VR system.
Yeah. Well, I mean, before we go on a tangent of the more fascinating details of your research, do you mind telling the audience that what exactly is neuroimaging?
So neuroimaging, is a very broad term. It's really an umbrella term, which is any kind of modality that allows us to gain imaging data and to visualize what's going on inside your head.
That's something that we all wondering about, right? What is going on in our brain? What do we do? What we do?
Yes, of course.
Yeah.
And there are lots of different modalities actually that one can use for neuroimaging. They're all very complementary because they give lots of different kinds of information, and there are pros and cons to each one of those methods, right? So the major tool that I use is magnetic resonance imaging.
Yeah.
Which gives you very nice information about the whole brain. It's safe, there's no radiation, but the downside is you have to stay still while you're having an MRI scan. You can't have any metal or anything that's affected by a magnetic field when you're having an MRI scan, and it's extremely expensive.
Yes, of course.
And on the other end of the scale, then you've got other things like, for example, ultrasound.
Yeah.
Where ultrasound doesn't give you nearly the same kind of detail, but it's very cheap and portable.
Yeah.
Anyone can use an ultrasound machine.
Yeah.
And so you can imagine that there are different pros and cons to those things, but they're all giving you complementary information about the brain.
Yeah, and there's also the EEG that we just mentioned as well.
And then there's EEG, there's other things like MEG, magnetic encephalography, and near-infrared spectroscopy. So there's numerous methods basically that can be used.
For the purpose of this episode, we can't really introduce of all the different methods of the neuroimaging. Do you mind just telling us how exactly does an MRI machine works?
Sure. So essentially, an MRI scanner is a very large superconducting magnet. Yeah. So that's where we'll start from. Okay. So if you look at an MRI scanner, it looks like a tunnel. And it's inside a special room. Yeah. And when you go in, you can hear a sort of pumping noise in the background, and you can see that there are lots of different kinds of computers and things all around it connected to it.
Yes, of course.
But the very basic structure of the scanner is that thing that looks like a tunnel is effectively just a very, very large magnet. Yeah. Standard MRI scanners have a magnetic field, so the strength of that main magnetic field. Yeah. Which is something like what's called 1.5 Tesla or 3 Tesla, where Tesla is the unit of the strength of the magnetic field. Yeah. Just for comparison's sake, the strength of the Earth's magnetic field, I don't know this off the top of my head, is something like 0.000003 Tesla. Okay. So it's obviously significantly smaller. Yeah. And if you were to walk in, with a coin or a small piece of metal into the presence of the MRI scanner, it will actually just go flying straight into the scanner and get stuck to the scanner. So it's an extremely strong magnetic field. Yeah. But that said, it's as long as you're using it in the right conditions. And so you're not going in there with a coin or metal, then it's an extremely safe modality because there's no radiation. Yeah. And it's completely non-invasive, so you're not having to put any implants, or you're not having to do any operations or anything like that for someone who goes in the scanner. They effectively can lie down on the table and move into the MRI scanner and then be studied. Yes, of course. Yeah. So effectively what we do is that all of our bodies are made up of obviously loads and loads of different cells. Yeah. And then those cells will contain various different chemicals and various different kinds of molecules that are making up the body. by far, of course, the most abundant element inside a body is going to be hydrogen.
Yeah.
And what we know is that hydrogen it's basically an ion. It's unbalanced.
Mm-hmm.
So it's got a single electron, single proton.
Yeah.
And that means it has a charge.
Yeah.
And basically, the very basic principle of MRI
Mm-hmm.
is that when you put these charged ions in the presence of a large magnetic field,
Yeah.
then they effectively act like tiny little magnets themselves, all of these hydrogen ions, and they will align with the main magnetic field.
I see. Yeah.
And what we can do then
Mm-hmm.
is that we can then manipulate the way those hydrogen ions behave inside the main magnetic field,
Mm-hmm.
and we do that by applying radio waves.
Yeah.
And by doing that, then what it means is that we can manipulate it in a way that we control.
Yeah.
And by doing that, then that means that we can then study how they behave differently depending upon what configuration and I suppose what kind of cells or what kind of molecule the hydrogen is in.
Mm-hmm.
So you can imagine that if you have hydrogen ions inside water,
Yeah.
then it will be very different to where it's a very stable kind of configuration that the
Yes,
hydrogen is
yeah.
in, because there's two hydrogens with each oxygen and they're very tightly
Yeah,
bound
the
together.
bonds is closely linked together.
It's very different to when it's inside fat, for example,
Mm-hmm.
or if it's inside different kinds of other things like proteins or different kinds
Yeah,
of
that
cells.
makes sense. Yeah.
And so what that means is that when we apply these radio waves and we change the magnetic, the way the hydrogen ions are behaving inside the main magnetic field, then it means that they'll be slightly different depending upon the different kinds of state that they're in,
Yeah.
and that means that will generate different kinds of contrast for our image.
I see. Yeah.
So when we read out the signal that comes back
Mm-hmm.
from whatever's inside the scanner, then we can measure the differences in the properties and convert it to an image.
Mm-hmm. Makes sense. So we briefly touched on about like how like the usual one is either like 1.5 Tesla or 3 Tesla. So we talked about like how the research you're working on the 7 Tesla is like give you like the fascinating of the details, but how exactly does different field strengths really affecting the resolutions of the signal you're getting from it?
Yes, so basically we work with these standard field strength scanners.
Yeah.
Partly because, I mean, this is just the preface to it, partly because they are more affordable.
Yeah, obviously, yeah.
And more generally available, which means that, across hospitals across the country, they'll be working on those kind of field strengths. So, of course, what we want to do is we want to do research that tells us about the brain, but also something that can be used and can be generalised across different centres, right?
Yes.
When we're working with ultra-high field, we're very proud to say that we're one of the few places in the country that has an ultra-high field scanner. So the first thing to say is that obviously these methods that we're doing are really giving us exquisite detail, but they are a very particular kind of case.
Yes, of course.
That we're using them for. And the one thing to say is that as we move to ultra-high field, you give with one hand and you take with the other, as with everything, right?
Yeah,
so we
it's
get
always
more
a
detail,
trade-off, yeah.
but there are more and more challenges in terms of the fact that you might see that the image becomes slightly more warped. And the reason that the image becomes more warped is because when you move to the higher field strength, then what you have is more sensitivity to slight variations inside the magnetic field.
Yeah, of course. Yeah.
And also those slight variations in the magnetic field that are caused by something being inside it.
Yeah.
Like a body.
Yeah.
Or like different body parts.
Yeah.
And the other thing is that the higher magnetic field strength obviously generates more or different kinds of safety things that we have to think very carefully about.
Yes, of course. Yeah.
And the amount of testing that's been done for that has been different. That said, your question firstly, Patrick, that was asking, I just wanted to preface
of
because
course,
otherwise the first thing is everyone would say, why aren't we all using ultra high field scanners?
Yeah, makes sense. Yeah.
But in terms of what it actually means, so if we go back to when we were talking about how the scanner works in the first place and how you put some hydrogen ions in there, they align with the magnetic field, and then we look at what happens when we give them some energy with radio waves. And then we generate contrast, basically, when the signal is emitted back from those hydrogen ions. The amount of signal that will come out will differ based on the main magnetic field, effectively.
Yes.
Okay, so, and the more contrast we will get, will again depend on the main magnetic field, because as things recover to equilibrium, it will be different with different magnetic field strengths.
Yeah.
And so if you've got a very strong magnetic field, you can imagine that the contrast will be higher because things will recover back to equilibrium much faster.
Yes, of course.
example.
Yeah.
And so what that means is that we get more signal, we get more contrast, and because we've got more signal and more contrast, we can image faster because we have less noise in the image, and that means we don't need to average as many times. Okay, so quite a common thing is what we do it all the time in science, is that if we want to take a reliable measurement, we repeat that measurement over and over again.
Yes. Yeah.
And by doing that, then we can be confident what the true measurement is, because each time we'll have a little bit of error in that measurement.
Yeah.
And the more averages you do, then you can remove that error and you can get an idea of what the real measurement is.
Yes, of course. Yeah.
Because at 7 Tesla or at ultra high field, we can get so much more signal and much more contrast, then we can feel much more confident that we've got a much more less noisy measurement.
Yeah.
And that means we can acquire faster, or you can acquire data at the same speed as what you've acquired at a lower field strength, but you can use that to get much more detailed images, which is what we do.
Yeah.
Does that make sense?
Yeah, definitely.
There are particular things that we can do at 7 Tesla. So there are particular what we call contrasts, or particular types of images that we can acquire at 7 Tesla.
Yeah.
Which are much, much more detailed than at lower field. And that's because the actual mechanism, the physics concept that underlies the contrast that we get, the signal that we measure for those particular kinds of scans, is entirely based on how susceptible something is to the magnetic field.
Okay.
So how easily it's influenced by the magnetic field.
Yeah.
And so the classic example of that, two classic examples are iron inside the body, which of course is very easily magnetized.
Yeah.
And the second thing is hemoglobin.
Oh, okay.
And so when we look at functional MRI, which is one of the things that I use a lot and something that's always been a personal passion of mine, what we're doing with functional MRI is we're looking at how the proportion of different types of hemoglobin, whether or not it's carrying oxygen or it's not carrying oxygen, change in different regions of the brain when it's doing some activity.
Okay. Yeah.
And effectively that hemoglobin behaves differently, or its magnetic properties are different when it's bound to oxygen or not.
Yeah.
Because the susceptibility of the hemoglobin changes.
Yeah. Yeah.
So if it is not bound to hemoglobin, then it's paramagnetic and it's much more susceptible to the magnetic field.
Yeah.
So it can be much more influenced by the magnetic field.
Yeah.
And if it's carrying oxygen, then it's a much more stable molecule, which means it's not so influenced by the magnetic field.
Yes, of course.
And so if there's some activity inside the brain, then what we tend to see is that oxygen rushes to that region of the brain and the magnetic signal changes.
Yeah.
And you can imagine if you go to ultra high field, then we've got more signal because that's the mechanism that creates it. So functional MRI is something that is very clearly benefiting from moving to ultra high field.
So we just talked about how different field strengths, and then you talk about the applications in fMRI. So what exactly is fMRI differ from like the structural MRI per se?
So functional MRI, fMRI, is a way that we can study activity inside the brain. And it does that by effectively looking at how blood flow is changing in different regions of the brain. So when you are carrying out an activity, then the neurons inside your brain will start firing to allow the brain to start processing whatever's needed to be done. And because the neurons need to be fed, then the blood flow increases to that part of the brain to deliver oxygen and glucose and all the good stuff that those neurons need to work.
Yes, of course. Yeah.
And so what we can do with the scanner is that we can measure how those differences in blood flow and oxygen supply are changing as a result of some kind of activity occurring.
Yeah.
The big advantage of fMRI is that we can then see that across the entire brain. So we can see it not just across the surface of the brain, but we can see it deeper inside the brain. And we can then relate the activity and the changes in blood flow from one region of the brain or one part of the brain to all the other parts of the brain.
I see.
And so we can see how the whole brain is working as a system, not just in that area alone where we can see a little bit of change in activity.
I see. Yeah, so it's a very different type of like system compared to just looking at the structural difference in brain. So how exactly does that apply to like a different research that you might be interested in?
Yes, of course. So if we're thinking about how the brain works, we can actually then think about, there are so many different applications, different questions you can start to ask, right?
Yeah.
When we are just sitting here talking to each other, our brain is ticking over, it's working all the time, right?
Yeah.
And so we have to be able to coordinate activity across all the different regions of our brain.
Yeah.
To take in that information, and then for us to feed it forward to be able to then use another part of our brain to then plan the next piece of activity and to carry out that next piece of activity.
Yeah.
With fMRI, what it means is that we can actually look at how this activity is changing over time, and we can see how the brain is processing different things that are being like inputs into the brain, shall we say?
Yeah.
So different kinds of stimuli like
the visual stimuli we were talking
visual
about.
stimuli, sound, touch, and all those kind of things.
Yeah.
And similarly, we can also think about then what kind of brain processing occurs when someone is responding to something, or if they're actually carrying out an activity, such as there are many people who did different kinds of what we call task experiments, where someone has to respond to a particular kind of a stimuli or a particular kind of question, and they, for example, are responding using buttons or making particular kinds of movements and things. And so then you can study how the activity changes to allow someone to be able to do those kinds of things. The other thing that we can do with fMRI is look at how activity is organised inside the brain, even when you're just at rest, you're not doing anything. Yeah. And that gives us very, very fundamental information about the way that the brain is organised. Yeah. And the way that the brain can then allow us to do other things. So what's its kind of what we call the resting state before it's preparing to do other things. And of course that can give you an idea of how that might be different in different kinds of disease populations, and of course how it's different through development as well.
Yeah, like one of the major topic is the mind wandering of how that affect during the brain activities. So that's what I heard is one of a lot of study has been doing on that in resting state neuroimaging. Yeah.
Yes, exactly. So things like mind wandering and how the brain and its activity is just drifting away at rest.
Yeah.
What people often do is they study what's called functional connectivity, which is when they say what's the organisation of activity? How is one region of the brain talking to another during mind wandering or during just when someone is just at rest? And how does that dynamically change? How does that change with time across the period that someone's being scanned or across the day?
Yes, of course.
And again, you see that gives us very kind of fundamental information about how the brain is working all the time.
Yeah. So we were talking about the fMRI is still working in an MRI machine where you just lay down and then either resting state or focusing on the stimuli that was presented to them. So how is the fMRI more advantageous to the other medium like EEG or other type of neuroimaging technique where you can actually do the movement in terms of tasks? Like, why would we choose fMRI instead of just the more portable versions of the neuroimaging techniques?
Yeah, so that's a very good question, Patrick. So I think all of the methods are very complementary. Yeah. That's the first thing to say. And I think that what you want to do if you're doing a neuroscience experiment, and specifically one that's looking at activity, neural activity, is you want to use the right modality for your question. Yeah. The big advantage of fMRI is that basically you'll get activity across the whole brain. Because if you're using something like EEG or near-infrared spectroscopy, you're recording activity from the surface of the brain, and you won't have any idea about what's happening in the deeper areas of the brain, like the thalamus, the hippocampus, and the areas across the base of the brain, which we know are very, very important for different kinds of things. Yeah. And so that's one clear advantage. The second thing is that we can also see the activity being integrated across the whole brain. And so we can see not just whether or not there is activity in those deeper regions, but we can also understand the relationship between that activity with what's happening on the surface of the brain as well. And then the third thing is that you can relate the activity that we can see on the fMRI with the other information that we've got about the structure of the brain during the same acquisition. Yeah. So you can measure with MRI because it's a very flexible modality. You can measure, for example, the shape of the brain. You can measure the volume of different regions inside the brain. Yeah. You can measure the signal inside the white matter connections inside the brain. And you can even measure the levels of chemicals inside the brain or the neurotransmitter levels inside the brain. Yeah. And so you can imagine it's extremely powerful when you start to combine all those things together to give you a much more comprehensive picture of what's happening inside the brain and how it enables activity. Conversely, as you say, if you were going to use EEG or something like optically pumped MEG, then you can have someone who's doing something which is a bit more active and mobile outside the scanner. And it's obviously a little bit cheaper as well, and you're not so sensitive to motion in the same way like you are with MRI.
Yeah.
But you're then having the trade-off of having this deeper information about understanding how the brain works as a system and across the entire brain.
Yeah.
And so what you gain there, you're losing, I would say, in spatial specificity and systems knowledge. So I think it's just about identifying the right questions for your tool, or conversely the right tool for your question.
Yeah, of course. Well, yeah, so I mean, we know that MRI machine can do a lot of stuff, but I mean, I had a pleasure to be an participant in one of the MRI study. The noise is quite similar to what I would experience from like the airplane, and there's like the old article from the Guardian stating that it's the whole MRI machine is kind of the claustrophobia induced experience. Is it really that scary for like someone who never experienced going into an MRI machine to do the scan?
So I think as a starter, I suppose the point is that yes, I suppose it can be a little bit claustrophobic, right? It is quite odd experience, right? You're asked to lie down on this table, slide into this kind of tunnel, and then as you say, you've got some noise going on in the background, and then you're just lying in there and you're not really sure what to do the first time you have it. I think, should we say, frequent flyers like myself that have had lots of MRI scans, you tend to fall asleep because you realise it's a fairly mundane and innocuous thing that happens. But I think for the very first time, especially if you're someone who has claustrophobia, it might be quite anxiety inducing. The trick really to getting around that, and I think it's particularly with children, is trying to find ways of distracting someone while they're in there. And if we can do that by distracting them either both visually and also with sound and stuff like that,
course,
then what that means is that they can just be more comfortable and they can become less aware of the disturbing things around them. Traditionally that's been done with playing music through headphones, and alternatively by showing something like a movie which you might watch through like a mirror. That's just
it's like a fairly small screen that in front of me or something like that.
Yes, exactly. And then you could just watch a movie and then carry on watching that movie, and you might be distracted while you're in there. That strategy is relatively successful, and that's certainly what they would do in lots of different hospital settings and for lots of different studies. The downside is, of course, that you are still quite aware that you're lying inside this funny tube because you're only looking at this tiny mirror. And so that kind of leads us on to why we have put a lot of effort into designing an MR compatible virtual reality system that can really make you immersed and distracted. And one of the things that's really been exciting since we've invented that system is that we've seen that people are really just not aware of where they are when they're doing it. So it's light tight, so you can't see anything around you. We've got noise cancelling headphones on that the people are wearing when they're using it. And because they're enjoying using this VR system, then they're just not aware of where they are and what's going on around them.
So it's like the whole immersive experience that's sort of separate from what they are experiencing inside the MRI machine.
And we've been able to scan actually children as young as 2 years old with this, where they've just really not even noticed where they are, that they've just been very happy using this virtual reality system and not even noticed that someone's moved them into the MRI scanner and that there's been this noisy machine working in the background. So that for us was very exciting to see, very rewarding to see, because we spent a lot of time developing that system.
Brilliant. A major part of your research is focusing on baby or like prenatal stage. Why specific this kind of like a range of the scan that you're interested in? Like instead of let's say adolescents or old adults, like personally for you, why are you interested in looking at baby and prenatal outside of all the different kinds of the age range you can scan to?
Okay, yes, well, I mean, it's very much largely motivated by my clinical practice, right? So I'm a consultant in the Evelina Children's Hospital in paediatric neurodisability medicine. So I look after children who unfortunately have got long-term difficulties because of them suffering brain injuries very early in their lives, And I also spend a lot of time in the fetal medicine unit, speaking to families who unfortunately have received bad news about their baby's brains.
Yeah.
And so for me, developing those methods to be able to aid my clinical practice is very important.
Mm-hmm.
And I think that was really a major motivator, because when I started training in paediatric neurology, I realised actually that there was so much that we didn't know,
Mm-hmm.
and in a way so much better that we could do in terms of being able to understand what was happening in the brains at this time, and that a lot of the treatment that we were doing is very it's still based on very old knowledge,
Yes,
and it's very reactive. So it's not based on any kind of mechanistic insight about what happens in the disease process. And that kind of motivated me when I started doing my research in 2007.
Mm-hmm.
I'd been working as a doctor for 6 years then, and that kind of motivated me to say, okay, actually I really would like to be able to do something differently.
I see, yeah.
And to try and make things better. On the flip side to that, taking my kind of medical hat off, the other thing to say is that it's an absolutely fascinating time, right? Because the brain at this stage is developing so rapidly and changing so rapidly that there's just so much to study and understand.
Yeah.
Because these things, it has implications for the rest of our lives, but it's also something that's very, very fundamental.
Yes, of course. Yeah.
In terms of how the brain is put together, right? And understanding how the brain's put together will give us an understanding of ultimately how the brain works and why it is the way it is.
Mm-hmm.
So, I always like to say that there's this very famous quote by Papin Wigglesworth, I believe the name of the neuroscientist.
I gotta be honest, I have no idea who that is.
Where they said that the brain of a basically like a 28-week fetus and 36-week fetus or a preterm infant is much more different than a 2-year-old and an adult, basically.
Yeah, makes sense. Yeah.
Because just in that 6-8 week period, the brain is changing so much. It's increasing in size, but the brain is folding across its surface. You've got different connections being made inside the brain. And different structures are emerging and connecting together, and so it's a really fascinating and key period to study, and that's of course the other major motivation for the work that we do. And then the last thing to say, sorry, I'm going on.
No, it's absolutely, yeah.
The last thing to say is that if you just think about behaviour and how your behaviour changes, right? Then, as you say in adults, well, why don't you study adults? Well, adults, what you're looking at is you can look at psychological constructs, and you can look at fixed ranges of behaviour. Yeah. But those things, in effect, are set, right? In the adult,
it's quite fixed already. Yeah.
Whereas, and still, we don't know, despite the fact all the imaging and all the different studies that are done, we still have, we struggle to understand what is the brain processing and the regions of the brain that are involved in very fundamental things in everyday life, right, in adults.
Yeah.
So actually if we just take a step back, what would make more sense is to say, okay, what we should probably do is we should be looking at what's changing inside the brain when these behaviours emerge, right?
Yeah.
If you look at what happens in a child across their first 10 years, shall we say, this is when they are completely changing in terms of what they can do and how their brain is allowing to do stuff, right?
Yeah.
So they start from being a very kind of shall we say, a passive being at the start, where they are lying there, the environment does things to them. Yeah. To then understanding that they can interact with their environment, that they can influence their environment.
Yes, of course. Yeah.
To then understanding consequences and being able to plan how they interact with their environment, understanding reward, understanding the wider context and the influence of their behaviour on other people. Yeah. And all those things are just gradually developing and keying in as they're growing older and older. Yes. And so as those skills are emerging, then obviously it's really fascinating to understand how the brain is changing to enable those things to happen.
Yeah. Well, last question for this segment. Of all your time as a head of department and then supervising all the students, what kind of people do you think might be really interested in studying neuroimaging or neuroscience? Even before they realize what kind of personalities or what kind of interest they natively have might lead them to kind of this route you're going now.
So actually, I don't think there is any particular kind of personality, right? I think the important thing to say is that actually what's changed the field and what continues to change the field is actually incorporating the skills, experience and interests and questions that everyone generates.
Mm-hmm.
You know, my lab group contains people who are working in neuroscience areas, but we also have people with backgrounds in mathematics, engineering, and wider across the department. Of course, we've got physicists, and we've got people who are working on the brain, but actually their background is something completely different. And it's very interesting because then they think of how the brain works and what we could do with studying the brain in a completely different way from someone who is just a neuroscientist right from the start. And so I think we shouldn't be limiting ourselves to saying particular kinds of people or particular kind of skill sets. So similarly, I think, you know, thinking, it doesn't necessarily even have to come down to whether or not someone is scientific or mathematic. I mean, I think if someone is creative, and I think they've got plenty to offer as well, because I think they've got different ways of thinking or understanding or questioning what's going on inside the brain. So I think that there's lots of different perspectives, and I really welcome people from any kind of perspective to try and get into neuroscience and to understand the brain.
Okay, that's all the time we got for this episode. Tom, thanks again for coming by for this podcast. Today we covered the basis of MRI, the applications and the use behind it. In our bonus episode next time, we're going to talk about the science communications working in neuroscience. So do check it out if you're interested. Take care, everyone, and until next time.